In this video, we're going to discuss slope of a surface in the x and y directions. So let's say we've got a surface that's represented by z equals f of xy. So for every xy in the domain, we associate a particular z value with that. When I map that for every xy in the domain, I end up with a surface. Maybe it's something like this, and it's up here. If we're interested in the slope of the surface in the x direction and the y directions at a particular point, basically we're going to take a plane and intersect it with a surface that goes through that point. So let's say I want the slope in the x direction at x naught, y naught. So maybe this is my x naught, and this is my y naught over here. That x naught, y naught is associated with a particular z naught. Maybe that z naught is right here. This is x naught, y naught, z naught. Now, if I want the slope of the surface in the x direction, what I mean is, if I am at this point and I head entirely in the x direction, so I'm not heading in the y direction at all, what happens to the z values? To figure that out, I intersect the plane given by y equals y naught. So the plane that passes through that line right there. And this is a plane that's parallel to the xz plane, so it might look something like this. And I find out where that plane intersects my surface. And maybe it looks like that, roughly. This is the plane given by the equation y equals y naught. Then I find the slope of the surface as x increases in that or I find the slope of the surface, or the change in the z values, as x increases. So it's just like a regular Calc 1 derivative, but it's just a Calc 1 derivative on this curve, and I'm going in the positive x direction. I feel like I need another color, so let's get another marker out. So I'm looking for the slope right here. What's that instantaneous change in z as we head in the x direction? Well, to figure that out, we compute the following. This is called the partial derivative of f with respect to x. I'm going to use WRT to abbreviate with respect to. This is notated this way. It's the partial of f with respect to x. It looks like a backwards 6, but that's not a backwards 6. It's also not a delta. It's a partial sign. I'm interested in that partial at a particular x naught, y naught, because that was x naught, y naught, 0 right here in the xy plane. We found the corresponding z value on the surface. So I want this partial at x naught, y naught, or sometimes we use subscript notation. That's the partial with respect to x of the function at x naught, y naught. And that's given by this. We're taking a small step in the x direction, and we're on the plane y equals y naught because we don't want y to change at all. We're just wanting to see what happens to the z's as x changes. So I let x change, and I take the limit as that change in x goes to 0 to get the instantaneous change in z as x changes. So back in Calc 1, we had delta y over delta x. This time we're going to have delta z over delta x. So we'll have f evaluated at x naught plus delta x minus f evaluated at x naught, all divided by delta x. And the y's are staying the same because we're on that plane and we don't want y to change. We just want to know what happens to z as x changes. So y is y naught in both of these. Now we're not going to actually use this derivative definition. this limit definition of the derivative, but it does indicate the process for finding the partial derivative of f with respect to x. What we did was we treated y as a constant because we're holding y constant. We're forcing y to equal y naught, and then we're saying, okay, how do the z values change as x changes? We're holding y constant, and then we're differentiating with respect to x, and then we're plugging in x naught, y naught. So that is, in practice, how you compute the partial derivative of f with respect to x. And I tend to use subscript notation just because it's fast. Either notation is fine. I love this notation when I'm talking about applications because it reminds me that I'm going to interpret it as the instantaneous change in this as this changes by 1 unit at a particular point. But this subscript notation is great when I'm just doing calculations. So if I want to compute the partial of f with respect to x, we treat y as a constant because we're on this plane where y is equal to a constant. And then we differentiate with respect to x. And that's it. And most students are very comfortable with this definition. It's just a little bit harder in practice. Sometimes you see a y and you want to differentiate it because that's what you're used to doing. You just have to hold off and remember you're treating y as a constant and differentiating with respect to x when you're taking the partial of f with respect to x. So that's partial with respect to x. You can imagine how this goes for the partial with respect to y. It's very similar. If I want the partial derivative of f with respect to y, and this is giving me slope of the surface in the y direction, whereas this was giving me slope of the surface in the x direction at that point x naught, y naught. What I'm looking for here is the partial of f with respect to y. That's notated this way. Don't use df dy. Use this. As soon as you see that little partial sign, you know that this function depends at least on y and some other variables. We're holding the other variables constant. We're differentiating with respect to y. And then we're evaluating this at a particular point, x naught, y naught, to get a slope of the surface at that point in the y direction holding x constant. Or we can represent it this way using subscript notation. And that comes from taking a plane and intersecting it with our surface again. Now here I fixed the plane y equals y naught, and now I have a curve that goes in the x direction only, and I looked for the slope in the x direction. If I just look at this picture, from my picture it looks like the z's are going down as x increases. So I would say the derivative with respect to x is negative at that point. Now let's draw a similar picture for the derivative with respect to y. Well, here I want to treat x as a constant. So I want to intersect this surface with the plane x equals x naught. Maybe my plane looks like this. And it would go all the way over there. And so here's where my plane, my blue plane given by x equals x naught, intersects my curve, or intersects my surface. And now I am looking at that curve and I'm thinking about what happens to the slope, what happens to the z values as we head in the y direction. Now remember, the positive y direction is over here. So I'm looking for the slope on that curve as I go that way. And it looks like the z's are going down as y increases, so I would say the derivative at that point in the y direction is negative. Well, how do we do that? Using limits, we first take the change in f with respect to y. So we're going to force x to stay at x naught. Want that to stay exactly the same, and then we want y to change by a little bit. So we're going to go from y naught plus delta y, or from y naught to y naught plus delta y. So it's the change in z over the change in y. And then we're going to let the change in y go to 0. And that's the definition of the partial of f with respect to y. So this is giving me slope in the y direction. Partial of f with respect to x at a particular x naught y naught is giving me slope in the x direction. Slope of the surface in the x direction at x naught y naught. Now if I don't plug in a particular x naught y naught, these partial derivatives are giving me a formula for the slope in that direction. But once I plug in my x naught y naught, I actually get a number that tells me how much z is increasing or decreasing as x or y changes by 1 unit at an instant at that point. So again, this is the definition, but I don't generally use the limit definition when I want to take the derivative with respect to y. We're going to do the same thing that we did over here. If I want to compute the partial of f with respect to y, I treat x as a constant, and I differentiate with respect to y. And that will give me a formula for the slope in the y direction, and if I plug in a particular point, that can give me the slope of the surface in that direction. So here is our surface. By slicing it with a plane y equals y naught and seeing how z changes as x changes, we get slope in the x direction. By slicing that surface with a plane x equals x naught and seeing how z changes, we get the slope of the surface. I think I may have said that backwards. I slice the surface with the plane x equals x naught, and then I look at the slope of the surface in the y direction. I see how y changes. So this, when I look at the slope along this curve, that's giving me the slope in the y direction at x naught y naught. When I look at the slope of the surface along this curve, where y is fixed and x is changing, this is giving me the slope of the surface in the x direction. Positive x is coming out of the page. Positive y is going to our right because of where we're oriented relative to our right-handed coordinate system, because of the way we're looking at it. Okay, so that is the theory, and I think most people are very comfortable with the theory. We're going to start with a very simple example, and then we'll interpret it, and then we'll do a more advanced example, something that's more likely to show up on a quiz. So let's do simple example. So let's say we have z equals 5 minus x squared minus y squared. Hopefully you know what that looks like. Z is raised to the first power, x and y are both squared. So I know since both of these are squared and z is raised to the first power, I either have an elliptic paraboloid or a hyperbolic paraboloid. So I'm either looking at a saddle or something that looks like a parabola in 3D. Since both of these have the same sign, it's the parabola one. It's the parabola in 3D, which is called the elliptic paraboloid. Now if it was z equals positive x squared plus y squared, it would be an elliptic paraboloid facing up. But I took that and I multiplied by -1, so that flipped it upside down, and then I raised it up 5 units. So this looks like this, roughly. When x and y are both 0, z equals 5. And this continues on. It goes beyond the xy plane, but I'm just drawing it to there so that we have some sense of the surface that we're looking at. when z equals 0, we get 0 equals 5 minus x squared minus y squared. So this is a circle of radius square root of 5. So we go square root of 5 units in the x direction, square root of 5 units in the y direction, plus or minus. So this radius is just a little bit more than 2. This is not to scale, clearly. Okay, so now let's say I want the slope of this surface in the x direction at the point x equals 1, y equals 2. Well, that's going to be the partial of f with respect to x at the point 1, 2. So I go 1 unit in the x direction, 2 units in the y direction, and I find that point on the surface. When x equals 1 and y equals 2, we've got 1 squared minus 2 squared. Wait a minute. Z equals 0, so we're actually going to be right there. I don't want that point. Let's plug in a different point. Let's substitute in x equals 1, y equals 1. So at x equals 1, y equals 1, z is going to equal 3. So I have z is f of xy equals this. If I substitute in 1, 1, I've got 5 minus 2, which is 3. So we're going to go this way, and then we're going to go up 3 units. So that's a point on our surface, 1, 1, 3. Now if I want the slope in the x direction at that point, and remember those are 1s now, not 2s, what I'll do is I will intersect my surface with a plane given by the equation y equals 1. So it's parallel to this line, y equals 1, my plane is. And then I'm seeing where that plane intersects the surface. And I think what we're going to see is something that looks like this. It's actually going to be on the other side, probably in the bottom. Sorry, that's not a great picture. But yeah, we're going to have a curve we're going to have a plane that's intersecting our surface, and we want to find the slope of that curve in the x direction at that point. Well, according to calculus, according to just our regular computation or rules of computation, the partial of f with respect to x, or sometimes we'll notate it this way, the partial of z with respect to x, it's the partial with respect to x of 5 minus x squared minus y squared. Derivative of 5 is 0 with respect to x. Derivative of x squared is negative 2, negative 2x, excuse me, with respect to x. And we're treating y like a constant. So this might as well be a 3 squared. It might as well be a negative 9. The derivative of that constant with respect to x is 0. So the slope of the surface in the x direction is negative 2x. If I want the slope in the x direction at x equals 1, y equals 1, I have to substitute in x equals 1, y equals 1 to this function. So the slope in the x direction, which can be written this way, or if you prefer it can be written this way, that's totally fine, is negative 2. And what does that mean? That means instantaneously at that particular xy pair, as x increases by 1 unit, z goes down by 2 units. So the slope is negative 2 at that point on the curve. Okay. And if I want the slope of the same curve in the y direction, I think we all know how that's going to turn out. I will intersect a plane given by x equals 1, through my surface, and then I'll look at the slope in the y direction at that point. the slope of in the y direction is given by the partial of this function with respect to x, or with respect to y. Derivative of 5 with respect to y is 0. Derivative of negative x squared with respect to y, there's no y in it, so it's also 0 because we're treating x like a constant. And then the derivative of negative y squared with respect to y is 2y. So the slope of the surface at 1, 1 in the y direction is negative 2 times 1, so negative 2. So the z's are going down. Our z's are decreasing by 2 when y increases by 1 at that point instantaneously. Okay, so that's a very simple example, and I'm sorry that my picture wasn't better. I did the best I could. But I hope you get the idea. I'm taking a plane and I'm intersecting my surface with that plane, and then I'm looking at the curve that results from the intersection of that plane and the surface. Okay, so here's a more advanced example. So let's say I want to find the slope of this surface in the x direction at x equals negative 2, y equals 1. Oops. Sorry guys. X is negative 2, y equals 1. Well, that's going to be the partial of f with respect to x evaluated at negative 2, 1. So first I need to take the partial of f with respect to x. So I've got a product here. That's my first function and that's my second function. Since I have a product, this depends on x and this depends on x, I'm going to use the product rule. Now if there was no x here, I would treat this first function as just a constant, so I wouldn't need to use the product rule. But since I've got a function of x times a function of x, a product rule is appropriate. So we'll take the derivative of the first function, it's a partial derivative with respect to x, treating y as a constant, times the second, undifferentiated, plus the derivative of the second function times the first function, undifferentiated. I just leave it alone. And then I compute this derivative and I'm done. Then I've got a formula for the slope at any xy in the domain. Now the derivative of this piece with respect to x, well, it's this. Derivative of x squared with respect to x, according to the power rule, we bring the power down, multiply by x to the 1 less power, 2 minus 1 is 1, and then we're adding the derivative of 3y squared with respect to x, treating y as a constant. Since y is a constant, this is just a constant with respect to x. The derivative of a constant with respect to x is 0, so that's gone. Now over here, I've got I wrote a y. I don't know why I wrote partial with respect to y. Over here, I've got an exponential with a function of x inside. So I'm going to have to use the chain rule, where this is my inside function. All right. The derivative of e to some power turns out to be, by the chain rule, e to that power times the derivative of the inside with respect to x, treating y as a constant, by the chain rule. And the derivative of the inside turns out to be negative 2x, and the derivative of the negative y squared is 0 because it doesn't have any x's in it. So this is our derivative. I've got a 2x times the exponential over here, and a negative 2x times the exponential times that polynomial. I think I'm going to pull that polynomial out front, in front of the exponential. And that's our partial of f with respect to x. That's a formula for the slope of the surface in the x direction at any particular xy pair. Now if I want to know what the slope of the surface is at this point, I need to substitute in x equals negative 2, y equals 1. Now you don't have to factor it at this point, but it's going to help to factor it it's going to help us to practice factoring, because we're going to need to factor a lot later when we are finding mins and maxes of surfaces. We're going to need the slopes and the x and y directions to both be 0, so factoring is important. So I'm going to look at this guy and this guy, and I'm going to say to myself, what do they have in common? Well, they both have a 2x. They also both have an exponential. And then I ask myself, this times what gives me this first function? It's just a 1. And then I ask myself, this times what gives me the second function? I have a minus that's missing, and this quantity x squared plus 3y squared. Now that's in parentheses, so that negative needs to be distributed to both of these. Okay, so that's my factored form of the partial of f with respect to x. So let's evaluate it at the given point, -2, 1, to determine the slope in that direction. So I've got 2 times -2 times e to the -2 squared minus 1 squared, all multiplied by 1 minus x squared, so that's -2 squared, plus 3 times y squared, that's 1 squared. So I've got -4 here. This is e to the, well, that's a 4. That's a 4 minus a 1, so it's -4 minus 1 is -5. Over here I have 1 minus, that's a 4 plus 3 is 7. So I have a -6 times a -4, that's positive 24 times e to the -5th. So that is the slope in the x direction at that point for this surface. And if we want, we could get a decimal approximation. I'm not going to, but I'll just write it this way. Just to remind myself, e to the -5th is a positive number, so this is a small positive slope in the x direction at this point. If I want the slope in the y direction, I do pretty much the same thing. To find the derivative in the y direction, treating x as a constant, we have the partial derivative of f with respect to y. We'll have to use the product rule again. This is my first function, and this is my second function. We get derivative of the first times the second plus derivative of the second times the first. And of course, every time I say derivative, I'm talking about partial derivative with respect to y, treating x as a constant. Okay, so this, with respect to y, the derivative of x squared, if x is a constant, that's just a constant with respect to y. Derivative of a constant is 0. Derivative of 3y squared with respect to y is 3. Excuse me, times the derivative of y squared. So I bring my power down, I multiply by y to the 1 less power. So that ends up being a 6y. The derivative of an exponential, if there's a function of y inside, and there is, requires the chain rule. That's my inside function. The derivative of e to some power is e to that power. You plug the inside function back in, and you multiply by the derivative of the inside by the chain rule. Derivative of -x squared is 0, because there's no y's in it. The derivative of -y squared is -2 times y. So we have this. I've got 6y here times the exponential minus 2y times that x squared plus 3y squared times this exponential. And that's our partial of f with respect to x. Or excuse me, with respect to y. This is a formula for the slope in the y direction at any point in the domain of this function. Now if I want to set this equal to 0, we're going to want to do that later a lot. It's helpful to factor this. So I'm going to look at this term and this term, anything that's separated by a plus or a minus, because remember subtraction is adding the opposite. Those are separate terms. So I look at these guys and I think about what they have in common. Well, they both have a 2y, so I'll factor that out. And they both have exponentials, so I'll factor that out. And again, this is not necessary in this section, but it is appropriate and necessary in other sections. So we're just sort of practicing factoring for those future sections. So then I ask myself, this times what gives me my first term? The missing factor is a 3. And then I say, this times what gives me the second term? Well, I already have the 2y, I already have the exponential. I need the minus and the quantity x squared plus 3y squared. All right, so that's the partial of f with respect to y. Now, if I want the partial of f with respect to y at x equals negative 2y equals 1, which is giving me the slope in the y direction at this particular point, I substitute in y equals 1 and x equals negative 2. So I've got 2 times e to the negative 5, and this is still 7. 3 minus 7 is negative 4. So we have negative 8 over e to the 5th. So it looks like slope in the y direction is tiny and negative, and slope in the x direction was tiny and positive at that point for this particular surface. Okay. Now we talked about slopes, partial derivatives in the x and y directions. In another video we're going to find slopes in all directions. You don't have to go in the x direction or y direction. We could go in some other direction instead. We're going to do that in another video. But what we just found are called the first partial derivatives of f with respect to x. Since f depended on 2 variables, it has 2 first partial derivatives. The partial of f with respect to x and the partial of f with respect to y. Now the function also has what are called second partial derivatives. Sometimes people will just call them second partials. I can take the derivative with respect to x and take its derivative with respect to x again. That's the second partial of f with respect to x. I can take the derivative with respect to y, and I can take the derivative with respect to y again. So it's called the second partial of f with respect to y. Or I can take this derivative with respect to x and take its derivative with respect to y, so I get that mixed partial. That's what we call it when the variables are different down here, mixed partial. Or I can take the derivative with respect to y and take its derivative with respect to x. That is another mixed partial. So I think we're going to compute those in another video. But notice I've got 2 first partials and I've got 4 second partials because our function depended on 2 variables. Each of these guys, I can take their derivatives with respect to x and y again. Now, it's also possible that you could have a function like this. Technically, we could have a function of n variables, x sub 1 through x sub n. But here's a w. Usually we let w equal these functions. It has 3 variables. So w is going to have partials with respect to x, y, and z because w depends on x, y, and z. So we could notate those by the partial of f with respect to x, partial of f with respect to y, and partial of f with respect to z. Or we could use the subscript notation, f sub x, f sub y, f sub z. If we're talking about evaluating these at points, we could evaluate each of these at x naught, y naught, z naught. So this is telling me how w changes as x changes at a particular x naught, y naught, z naught. Now it's difficult to visualize because we can't even graph in 4D. So how can you think about how w changes as x changes, holding y and z's constant? But it's still instantaneous rate of change in w as x changes at that particular point. So even though we can't visualize it anymore, we can still calculate these things, and they still make sense. They still have real-world interpretations that are important. So there's some notation. If we're thinking of w as our dependent variable, sometimes we'll write w sub x, w sub y, w sub z to represent the partials of w with respect to x, y, and z. And we can also take second derivatives of this, and I think I'm going to take the second derivatives in a different video. So let's take some first partials. So I've got the partial of f with respect to x. This is pretty much exactly what you would expect. Now I'm treating y and z as constants and differentiating with respect to x. Now you do not have to show all these steps, but I'm going to show these steps just so that you can sort of see the rules in action. The derivative of the sum is the sum of the derivatives. So I can take the derivative of the first piece and then add the derivative of the second piece with respect to x, treating y and z as constants. Now over here, if y and z are constants, like let's say that this was a 9 times x cubed, the derivative of 9x cubed with respect to x requires me to bring down the 9 and then just take the derivative of x cubed. I can do the same thing with this yz squared. It's just a constant. Now, you might be very tempted to take the derivative of that. So if you can remind yourself that it's a constant and then factor it out, that may help. This is the derivative of a constant times x cubed. So I'll bring my constant down, and then I'll take the derivative of x cubed with respect to x. And this is constant. There's nothing there, no x's. Derivative of a constant with respect to x is just 0. So you could have also said, what's the derivative? You could have pulled this 2yz out and then left a 1, said what is the derivative of 1 with respect to x at 0, and gotten that same answer. But remember, y and z are constants, so its derivative is 0. Okay, so I pulled my constant out, and now I'm taking the derivative of x cubed. Derivative of x cubed is 3x squared. So I've got 3x squared, y, z squared. We tend to put the letters, the variables in alphabetical order. So that's our partial derivative of f with respect to x. Notice the difference between these two things, this one and this one. When I have a constant here, and there are no explicit x's listed, there's no x involved, the partial of this with respect to x is 0. When I'm taking a partial derivative with respect to x, and y and z are constants. Now over here, this is a constant times x cubed. So I bring my constant down and take the derivative of x cubed. A lot of students will start calling this 0 and this 0. It doesn't work that way. If there is an x there, you bring the constant down and take the derivative with respect to x, just like you would in Calculus 1 when you're taking a derivative. So that's how we take partials with respect to these various variables when there are more than 2 variables here. The partial with respect to x requires treating all of the other variables as constants. In this case, y and z are constants. And then we differentiate with respect to x. So let's just do one more. Let's take the partial of f with respect to y, treating x as a constant this time, and z is a constant as well. Now if this x and z are constants, this is a constant times y. The derivative of a constant times y is just the constant. Or if you prefer, you can pull the constant out and take the derivative of y with respect to y, which is 1. Over here, 2 and z are constants, so I can pull that constant out and take the derivative of y with respect to y. It's also 1. So we get x cubed times z squared plus 2z, and that's our partial with respect to y. Now the partial of f with respect to z comes from taking the derivative with respect to z of x cubed yz squared plus 2yz. Very similar. X cubed and y are constants, so I take them and I pull them out. And then I'm taking the derivative of z squared with respect to z, so I get 2z. And then we tend to list everything in alphabetical order and put the numerical factors first. So we'll do 2x cubed y times z. Plus, this is the derivative of a constant times z. It's just the constant 2y. Or if you're not comfortable with that, you could pull out the constant and take the derivative of z with respect to itself, and that's 1. And you're going to get the same answer. It's just the constant. Okay, so this is instantaneous change in w with respect to x, y, and z in the x, y, and z directions, which is difficult to visualize because we can't graph this function of 3 variables. The graph would have to live in 4-dimensional space. But we can still think about instantaneous rate of change in w with respect to x, y, and z, holding the other variables as constants. Okay, so let's go back to what we started with. If we have z as a function of x and y, that represents a surface in 3-dimensional space. If I want the slope of the surface in the x direction, I force y to be equal to a constant, so y equals y naught, and I differentiate with respect to x. That means I'm finding the slope of this curve where y equals y naught intersects the surface in the x direction, and I'm finding out how z changes as x changes at an instant at that point. When I am finding the slope in the y direction, I'm forcing x to be equal to a constant. So I'm taking a plane, x equals x naught, and I'm intersecting that with my surface. And then I'm looking at the slope of that curve at that point in the y direction, and I'm saying, how does z change as y changes at that point? What's the slope there? That's giving me the slope of the surface in the y direction at that point. Now in practice, we're doing these two things. When I'm taking a partial of some function with respect to one variable, I am treating all other variables as constants and then differentiating with respect to that variable. So the derivative with respect to x, the partial derivative with respect to x, requires treating the y as a constant and z's and any other variables if there were other variables, and differentiating with respect to x. The partial of f with respect to y, oh, it's right here, requires treating the x as a constant and any other variables, and differentiating with respect to y. It's easy to do, or it's easy to think about these concepts, but in practice sometimes it's hard. If it does get hard, just start factoring out constants and differentiating what's left with respect to the appropriate variable. That sometimes helps students to correctly compute derivatives.